Okay, these are the 1.1 notes on properties of functions. This is the first section in chapter 1, which will be about different types of functions and graphs of functions and things like that. So this first part should be mostly review. This is stuff that we did in Algebra 2 quite a bit. And then some of the stuff towards the end might be a little bit new to you. So first, we are going to review interval notation. So this is when we talk about domain and range, increasing and decreasing parts of a function, etc., using brackets, which also would be a closed circle, or just a line is also like a bracket. So to indicate that a value is included in a set. So anytime you have a line, a closed circle, you indicate that with brackets in your interval notation. And we use parentheses or an open circle, or not, it would be a dashed line, would be the same as like an open circle if it was a graph, to indicate that a value is not included. And you always use parentheses when we are talking about negative infinity and positive infinity, because they are not a specific value that we can include. It's just an idea, meaning going on forever. So always, 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 the infinities have a parenthesis next to them. Then also a u. So like you're probably remembering this from the test and the extra credit. This was what the extra credit was doing domain and range. And there was a U in some of them. Indicates a union of sets. So a jump in the domain or range that continues later. So if we're going from like negative infinity to 2, and then we have a space in the graph and it starts again at 5 to positive infinity, we put a U in between to indicate that those are all part of the same graph, but there's just a jump in the domain or the range. So just a little bit of practice using number lines, because the coordinate plane is just a vertical number line and a horizontal number line. So if we were going to write these inequalities using interval notation, I'm going to start by graphing them on the number line, and then we'll write them as interval notation. So if x is greater than -3, I would put an open circle at -3 and indicate the arrow going to the right, everything greater than -3. If x is less than -6, I would have an arrow going to the left, indicating everything less than -6. I have open circles at both -3 and -6 because we are not including those values in our notation. So for interval notation, what this would look like is it is coming from negative infinity. So we would say negative infinity to -6. We don't include the -6, so we put a parenthesis. Then there is a jump in our graph. Then it starts again at -3 and continues infinitely. So that would be our interval notation for that particular inequality. Number 2, we have x in between two values. So this is going to look like this. Open circle at -4 because it's not included. We don't have an or equal to sign next underneath the inequality. And then we go up to and include -2. And the x is all the values in between those two. So in interval notation, what this would look like is open circle at -4, because we're not including that value. We put a comma to indicate that we are going to continue to +2, where we will put a bracket because we are including that value. Number 3, if I graph this, -1 is less than or equal to x, which is less than or equal to +5. And it's between those two values. So in interval notation, we would have a bracket, -1, comma, +5, bracket, because they were both closed circles. And then number 4, if I graph this first, x is less than -4 to the left, x is greater than 1 to the right. So in interval notation, this is coming from negative infinity, stopping at -4, jump, so we put a U, starting again at -1, not included, and continuing on to positive infinity. We will express domain and range of functions and relations using interval notation. So you should be using the parenthesis, the bracket, and the U to indicate domain and range on everything moving forward, unless you're instructed otherwise. Okay, so then we get to a couple definitions that we need to clear up so that we understand the difference between a function and a relation. So a relation is the more general term. It is any two sets of numbers that are related in any way. So like any set of inputs and outputs with literally like no restrictions on them. You can have any number of inputs, any number of outputs, and we just call that a relation because it's just a relationship with no real defining parameters versus a function. So a function is in a specific type of relation, which does have a rule. So a function, the definition, is that it's a specific type of relation where each input can only have one output. So every x can only have exactly one y paired with it. And we'll talk about that a little bit on the next page about these rules and how to identify if something is a function or not. Last thing is domain and range. So if you've forgotten these, you need to remember. Domain is all input values. So domain is all x values that are part of a relation. Okay, and so domain goes left to right. Left to right and always least to greatest. So you have to put it left to right and you have to indicate domain from the least value to the greatest value. Range then is all the output values. So all the y values that are part of a relation. So when we talk about range, we are talking about the y-axis, and we go from low to high. So low to high, from least to greatest, to talk about range. So here's our little handy dandy quick reference guide to figure out if something is a function. A relation is a function if no x values are repeated in the set. So whether that's ordered pairs, whether that's a table, whether that is a mapping diagram, you cannot have x values that are repeated. So if you ever see repeated x, then it is not a function. Repeated y's are okay. So let's add that. Repeated y's are okay. But no x values can be repeated. Okay, number 2, a relation is a function if the graph passes the vertical line test. We can just call that vertical line test. And what this test says is that if we have a graph, in order for it to be a function, you have to be able to draw a vertical line through any point on that function, and it would only ever hit one point on the graph. So like this example that I just drew is a function versus something like this does not pass the vertical line test, because if I draw a vertical line through this graph, it's going to hit more than one point. It's going to hit 2 points. So we would say it's not a function because it does not pass the vertical line test. Okay, third way to tell is that those are the big ones. So y values can repeat. I guess I just bundled these all into 2 rather than 4. So we're just going to X these ones out. We'll just have our 2 little cheat sheets because I made it way shorter than I thought. Okay, we're going to identify if each relation is a function and say why or why not using a justification from above. So we will look at number 1. When we have a chart or a mapping diagram, we want to pay attention to the x values. So in this case, we have no repeated x values, so we can say that yes, this is a function because there are no repeated x values. No repeated x's. Number 2, again, I have a set of numbers. I'm going to pay attention to my x values. In this case, there is a repeated x. That is a problem. Because what that looks like on a graph is if you have on graph -1, 5, and negative 1, 6, those are going to be right above one another, and it will not pass the vertical line test. So we can say, no, this is not a function because there is a repeated x of negative 1. Number 3. Okay, again, we've got a set of numbers. Look at the x values. That's what matters. You can see that there is a repeated y, but that doesn't affect the idea of whether or not this is a function. So because there are no repeated x values, we would say, yes, this is a function because there are no repeated x values. Then we have some mapping diagrams. What I like to do for these is write them as ordered pairs. So because you can more clearly see like what it's saying. So each of these in the left in the X box pairs with an item from the Y. So we have 1, 1 if we follow this arrow. We also have 1, 5. And then we have 2, 4. And then 3, 3. So now that I can clearly see the ordered pairs, I again am just looking at my x's. I have the repeated x value at 1, so I'm going to say that no, this does not represent a function because we have a repeated x of 1. Number 4, if I do the same thing and I pair each x with a y, my ordered pairs would be negative 5, 8, so that's here, 0, 9, which is here, and then 5, 9, which is here. So once I do this, then I can clearly see what's x and what's y, and I do not have any repeated x values. So I can indicate that this is, yes, a function because there are no repeated x's. And then we have some graphs. So we're going to use our vertical line test to see if these pass. And in this case, this looks like the example I did above. This does not pass the vertical line test because when you draw a vertical line in many places on this graph, it's going to hit more than one spot. So we would say, no, this is not a function because it does not pass the vertical line test. And you can just abbreviate that VLT and I will know what you mean. Number 7, I can draw a vertical line through any point on this function, even though it's wiggly, and it will only ever hit one part of the graph. So this is an example of a function because it passes the vertical line test. Okay, so then kind of the last part of this is using function notation and starting to become familiar with function notation. So we will use the notation f of x. You may also see like h of x or g of x or f of t if like you're talking about time and a graph is of a projectile or something like that. So it just means that the output is a function of the input. So whatever x is or t is affects your output, affects your function. So we say f of x or h of x or g of x or f of t. This means that the output value of a function, or the y value, the output, is dependent of the input value, which is x. So we will primarily use function notation moving forward. To find the value of a function at a point, and we did this a bit with piecewise functions, you plug in that value for x in your original function. So we're going to do a couple here to practice. Here's our function. We've got f of x equals x squared plus 8x minus 2, and it's asking us to find f of 6. So we would say f of 6 equals, and then wherever we see an x, we plug in 6. So 36 plus 48 minus 2 equals 82. So f of 6 is 82. F of negative 4, be super careful, especially when we're plugging in negatives. So f of negative 4, we're going to keep this negative 4 in its parentheses when we put it into our x, plus 8 times negative 4 minus 2. So negative 4, the quantity squared, becomes negative 4 times negative 4, which is positive 16. 8 times negative 4 is negative 32 minus 2. So we get negative 16 minus 2. F of negative 4 is negative 18. F of 6, this is a typo. Let's do f of 0 here. So f of 0, if we plugged in 0 for every x, we'd say f of 0 equals 0 squared plus 8 times 0 minus 2. So f of 0 is negative 2, which is also our y-intercept. So the y-intercept is the same as saying f of 0. What if we had something like this, f of 2x? You do the exact same thing. So we're going to say f of 2x equals, keep it in parentheses, 2x squared plus 8 times 2x minus 2. And then exponents, we distribute this to both terms. 2 squared is 4, x squared is x squared, plus 8 times 2 is 16x minus 2. So that is, if I plug in a variable and a number, I can find the value of that function if we had 2x, for example. All right. Domains of functions. We are often given functions and need to be able to recognize their domains, even if we can't see a graph. So this is kind of the next step up from Algebra 2, where you need to know kind of the shape of your parent functions and start to be recognizing the restrictions on domains of specific functions. So this will be something that, like, sometimes you'll have a graph, but you will also sometimes not have a graph and have to determine the domain of the graph and where we have issues or where the domain doesn't exist. So the implied domain of many basic polynomial functions is all real numbers. So all real numbers, which we usually say as negative infinity to positive infinity. That's how we notate all real numbers in interval notation. So like linear, these go from negative infinity to infinity. Quadratic, these go from negative infinity to infinity. Absolute value, so left to right, these are all going from negative infinity to infinity. So they have all real numbers for their domain. However, there are functions that have restrictions on their domains. So, what do I want to say? But some functions have restricted domains. And we have to be able to watch out for those and recognize those. Okay, so rational functions, where we have something like this, and radical functions, where we have something like this, often present domain issues. Why? Well, in a rational function, we cannot have 0 in the denominator. So anytime we have a 0 in the denominator, that point cannot exist. It is not possible to divide by 0. So we have to watch out for those rational functions. Square root functions, what happens if we have a negative underneath our square root? Well, we get an imaginary number. So we remember that square root of -1 is equal to I, meaning like those values aren't things that we can graph. So anytime we get a negative radicand, that's not something that we're going to be able to graph. So we don't include it in the domain of the function. So we're watching out for those when we graph. All right, so again, we're going to practice using algebra. Here's my little hint for you down here in the corner. This is sort of problem domains that we're watching out for. Okay, notice number 1. So this is 2 plus x over x minus 5. This is a rational function. Rational means it can be written as a fraction. So it is a fraction, and we have an x in the denominator. In order to figure out the restriction on our domain, we will set this denominator equal to 0 and solve for x, because that's going to tell us what we cannot have in our domain. So we are going to have a problem when x equals 5 in this denominator, because if we plug in a 5, we get 5 minus 5, which equals 0, which we cannot have. So this domain is going to be everything except for 5. And the way that we write that in interval notation, so if we think about our number line left to right, it is coming from negative infinity, right? Let's call this -5. It's coming from negative infinity. We'll have a little hole at -5, and then it's going to keep going, because the only issue is literally at 5. You can plug anything else in, and it's fine in that denominator. So our domain looks like this. Negative infinity to -5. Do not include the -5. We have a tiny jump. We still need a u. And then it continues to infinity on the other side. So basically this is saying include everything except -5. Now a square root gives us an issue when we have something less than 0. 0 is fine. You can take the square root of 0. It's 0. But you cannot take the square root of a negative and put it on a graph. So we need to figure out when this radicand, x plus 3, it has to be greater than, well, let's put it like this. Let's say x plus 3. When x plus 3 is less than 0, that's when we're going to have domain issues. So if we solve, move over the 3, move over the 3, we are going to have domain issues if x is ever less than -3. Because if you plug in something less than -3, then you're going to get a negative radicand, and that's not okay. So if we write this as a domain, so here's like -3, and we're talking about everything less than -3 cannot be included, meaning we can have -3 in it, and everything greater than -3 is fine. So as an interval, we would write this as -3, included to infinity. So any value, including -3 and larger, will be fine as part of this domain. Okay, look at this one. This is why we've done so much practice factoring. If we look at the bottom, hopefully you notice that this is a quadratic. We want to get this into factored form so that we can clearly see the two factors to figure out where we're going to have an issue. So I'm going to do my factoring. On the top, a times c. On the bottom is b. So 4 and 1. I'm going to rewrite this in factored form. X plus 4, x minus 1. Okay, these are the two places that if I solve for x, I'm going to see where I have problems. So I say x plus 4 equals 0. I'm going to have an issue when x equals -4. And x minus 1 equals 0, I'm going to have an issue when x equals 1. So x cannot equal 4, x cannot equal 1, because if I plug those back in, I'm going to end up with a 0. So practice, like plug it in and see what happens. You're going to end up multiplying by 0, which is going to turn your whole denominator to 0, which is not possible. So if I look at this on like a number line, I can have values from -infinity all the way to -4. And then again from -4 to 1, and then again to infinity. So in interval notation, what this looks like, -infinity to -4, the values in between 4 and 1, not including 4 and 1, 1 to infinity. So I would expect that you could figure these out and then write them in proper interval notation. So those are the big takeaways from this is being comfortable with domain and range, interval notation, what's a function, what's not a function, and then can you algebraically figure out domain issues on functions.